All right, so we're going to start with question number one for past paper for the AS level curriculum. It's paper 1-2, 2022. And yeah, we're just going to get started immediately by trying to highlight the keywords in this first question. Well, I mean, before that, it's proper to just like analyze the image and see what's going on first. So what we're seeing here is just a sphere that is descending downwards in a liquid medium. So we already immediately kind of understand that there is going to be some resistive and upward thrust relating to this question. So that's just our predictive model trying to understand the question before actually reading it. I mean, I think that's good practice. So just try to keep that in mind every time you see a question like popping up. Anyways, so let's just start reading. A sphere of radius 2.1 millimeter falls with terminal constant velocity through a liquid as shown in figure 1.1. Three forces act on the moving sphere: the weight of the sphere, which is 7.2 times 10 to the power negative 4 newtons, and the upthrust acting on it is 4.8 times 10 to the power negative 4 newtons. The viscous force Fv acting on the sphere is given by the expression Fv is equal to kRv, where r is the radius of the sphere, v is its velocity, and k is the constant. The value of k in SI units is 17, so it's a unitless value. Okay, take out our highlighters and start highlighting the key pieces of information. So I'm going to start with radius 2.1 millimeter, terminal velocity through a liquid, three forces, moving sphere, weight 7.2 times 10 to the power negative 4, up thrust 4.8 times 10 to the power negative 4. This expression right here, r is the radius of the sphere, v is the velocity, k is a constant, and k is equal to 17. Okay, so always start a question by highlighting and identifying the key words and also pieces of information like given values and units and whatnot, something similar to that. And okay, our first question: determine the base SI unit for k. Well, how are we going to begin with answering this question? Just identify what we're given. Most of you may have already been able to figure out where to begin. That is, obviously going to be using the expression that is given to us, which is KRV, right? Why? Well, we understand that FV, the radius, and the velocity is kind of given to us already in terms of its units, right? Because we already understand that the force, right? I'm going to start with force right here. We know that force will always have a unit, kilogram meter per second squared, as derived from this F equals ma. Always. That's simply just the unit for force. It's just better to remember it by heart, but if you need to determine what is its origin, it's going to be F equals ma. So kilogram meters per second squared. So what about radius right here? Well, radius is going to be measured in meters, right? Right here you have a sphere, you want to measure from its center, you're going to use meters, right? Remember SI units. For V, it's going to be simply the velocity. And what is the unit for velocity? That is going to be meters per second. Okay, so we're given the units for all of the three variables. We're only trying to determine the value, the unit for K, the SI unit for K. So we can just isolate K by rearranging our formulas. FV divided by RV, that's going to be equal to K, right? Now it's perfect to just place in and substitute our units. So kilogram meters per second squared divided by, remember, every time you see a fraction, it means divided by, right? The radius multiplied by the velocity, and that's just going to be meter multiplied by meters per second, right? This can be simplified to kilogram meter per second squared divided by meters squared per second. Now, when we are dividing two fractions, this right here is going to be flipped over, right? We're going to multiply it. Sorry, actually the division sign is going to become the multiplication sign. Then this fraction right here will get flipped, right? Reversed. The more technical way of saying it is just the reciprocal. Anyways, so kilogram meter per second squared multiplied, flip it, seconds per meter squared. It's pretty awkward. What we're going to do, change color, cancel out all the common variables. This is going to leave us with kilogram per second meters. All right? Or if we want to write it in a non-fractional way, that is going to be kilogram second to the power minus 1 meter to the power minus 1. So kilogram second to the power minus 1 meter to the power minus 1. Okay, that is perfectly aligned with the marking scheme over here. All right, so move on to the second question. Use the value of upthrust acting on the sphere to calculate the density P of the liquid. Well, we are going to identify the keywords here, and I think the most important keyword in this second part is going to be upthrust and also the word density. So we know that the upthrust is going to be equal to, well, it's given to us in the formula sheet. That's just the density right here. The density multiplied by the gravitational acceleration and the volume. So, what was it again? Sometimes I don't remember these formulas, you know. Yeah, okay. So density multiplied by the gravitational acceleration and multiplied by v. Okay, so what are we going to do with this? Well, we simply need to calculate the density, right? So we're going to rearrange for density, and that is G, V is equal to P. Okay, actually, before we even start rearranging the formulas, we need to just write down our values. So Fu is given as 4.8 times 10 to the power negative 4. Okay. Now we do this, we just write down all of our given values because we are then able to predict whether or not we are capable of rearranging the expression for the exact variable that we are looking for. So it's always just good practice to write down before getting ourselves confused, you know, looking back and forth different paragraphs, seeing if we have the exact variables we need in order to rearrange for the other variable that we're looking for. Okay, we know that G is equal to 9.81 meters per second squared. And the volume, what is the volume? Well, we're given a sphere. So what do you think is the volume of a sphere? You know that the volume of a sphere is given us 4/3 pi radius cubed. Okay, you should remember this from high school, or rather middle school. Okay, so what's going to happen? Just calculate the volume first. 4/3 pi. Now be careful here. R is the radius, but we're not given radius in terms of meters. Always work in SI units. Always. It's always good practice to do that. That's what I always do anyways. We're given in millimeters, and we know that millimeter has the prefix of 10 to the power negative 3, so it's actually just 2.1 times 10 to the power negative 3. So 2.1 times 10 to the power negative 3 cubed. What is that going to give us? If I quickly plug this into my calculator, this is going to be 2.1 times 10 to the power negative 3 cubed. That is 3.88 times 10 to the power negative 8 meter cubed. Okay, Okay, so we have everything that we need. Just plug in our values. 4.8 times 10 to the power negative 4 divided by 9.81 multiplied by 3.88 times 10 to the power negative 8. That's going to be equal to 1,261 kilogram meter cubed. Right? So according to the mark scheme, they want us to run it to the nearest hundredths place. So it's going to be 1,300 kilogram meter cubed. 1,300. To double check, we do indeed have the correct value. Moving on to the third section of this question. So on the sphere in figure 1.1, draw 3 arrows. So draw 3 arrows, Draw 3 arrows to show the directions of the force, where weight is W, upthrust is U, and viscous force is FV. Label these arrows, as those respectively. So, okay, going back to figure 1.1. So, where is gravity going to be acting? Or weight? It doesn't, even in liquid, right? Weight just, simply doesn't disappear. It's still there. It's just going to be accompanied with another force. But let's just focus on weight. Weight is going to be pointed downwards. So, W. So, when swimming through liquid, is it easier or more difficult than walking through air? Moving through liquid versus moving through air. Which is more difficult? You might actually. It's actually a very easy question. Obviously, walking in water is a lot more difficult than walking in air. So we know that it's always going to resist your motion, and it's going to be making your motion through your journey more difficult, right? So it's always going to be opposing you, actually. So you. Oh no, actually, since the ball is moving downwards, it's going to be opposing the direction of the ball, right? So this is going to be FV, or the viscous force. It's always going to be opposing your direction of motion. Also, we're going to have an upwards force, like an upthrust, due to the displacement of the ball in the liquid, right? So that's simply our 3 arrows drawn. Okay, so determine the magnitude of the terminal constant velocity of the sphere. So when the constant velocity term is thrown around, what we understand immediately is that the acceleration is equal to 0, and the net force is also equal to 0. What this means is that the sum of the forces, the sum of the 3 forces up here, U, FV, and W, will all sum up to 0. Okay? So W, the weight, minus the upthrust, the viscous force plus the upthrust is going to be equal to 0. I'm going to say plus. Why? Because when arrows are in the same direction, you add them together. Sorry. Okay. You see these 2 arrows right here? They are in the same direction, so they must be added together. W is in the opposite direction compared to both of them, so W must be subtracted from both U and FV. Forces are vectors, so it's very important to make sure you get their directions right. Okay, so this can also be written as FV plus U, because we moved this entire thing to the right hand side. Okay, so the weight, we know that the weight is given, All right, it is given as 7.2 times 10 to the power negative 4. Newtons. Now FV is okay. Look, FU is given. We know that. Sorry. So FU is given. It is given as 4.8 times 10 to the power negative 4. We used this in the last question. Now FV is unknown, right? So what we're going to do now is just determine FV, because we need that in order to find the terminal velocity. So what's FV? Well, FV is just K R V. Right, we're just gonna write down the expression for the viscous force, KRV. And actually, before doing this, we need to, there's a better way of doing it. So if we want to find FV, we can just start from here. W minus U is equal to FV. Okay, so the reason why I can't do this, I can't write FV equals KRV and just figure out V, is because the question is asking me for a velocity, and I don't even have the velocity yet, and I also don't have the viscous force. There are two unknowns, and when you have two unknowns in your expression, it's pretty much you're pretty much stuck, and you can't really do anything about it. You have to immediately just find another way of solving that question. All right, so we're given weight, that's 7.2 times 10 to the power negative 4. And subtracting that from the up thrust, that is negative 4. That's going to give us 2.4 times 10 to the power negative 4 newtons. So FV is now 2.4 times 10 to the power negative 4 newtons. All right, so FV is K RV, then FV divided by KR is going to give us the velocity, which is what we're looking for. So substitute in all our values, and it will be 2.4 times 10 to the power negative 4 divided by 17, because K is given up here. Remember, K is given here. Then multiply that by the radius, which is 2.1 times 10 to the power negative 3. What is this going to give us? That is going to be 6.7 times 10 to the power negative 3 meters per second. Yep. So 6.7 times 10 to the power negative 3 meters per second. That's our final answer. So it's simply, the important takeaway is just to highlight the keywords, make sure you get your units right. Like you're given in millimeters, convert that to meters. Always, that's the first thing you should do. Write down your values, write down your given values here. Always make sure to write down your given values. That's good practice. Right here. Right, and the successful use of Newton's second law. So thank you for watching this video.